Hi again. So I'll be talking today about machine learning and privacy. But let me start with two disclaimers. So first of all, the slides that you have are like really rudimentary. I did not prepare a good slide deck. So I'm going to be doing a lot of hand waving and kind of verbal explaining, maybe draw something on the board. So sorry about that, but that's kind of an incentive to pay attention to what I'm saying. The second thing is a little more important. So I'm going to be talking about machine learning, but not really in a very rigorous or precise or mathematical way. So later today, you're going to kind of hear machine learning presented like properly as a computer science discipline. The machine learning I'm talking about today is kind of how we do it on the street, so to speak. But it's what people actually do. So if it sounds like, if it's going to sound like all like super fuzzy and like imprecise and there are no theorems, it's because like there are no theorems on the street. Okay, that's it is what it is. So I'll try to give some perspective on this of someone who is actually trying to use it, and I'm working with some people who actually try to deploy it to solve problems. And unfortunately, and you'll understand a little bit why I say unfortunately, they have little time for theory. And a lot of time for like putting more GPUs into it. The purpose of my lecture today, of both of them, is to try to motivate why we actually need some theory of privacy in machine learning, and why the kind of ad hoc things that people are doing out there are unlikely to lead us to any kind of happy place. Okay. So machine learning. So what does it mean in my world? So it's not theoretical. It's this kind of thing, right? It's basically all driven by headlines about how it's taking over the world and how it's achieving this like amazing, incredible, crazy results in all kinds of tasks like natural language translation, speech transcription, image recognition, object recognition, and so on. And that's kind of how I got into this whole machine learning business, is by trying to understand. So what is it? What like when you see like all these like amazing headlines, what's actually happening underneath? And you keep seeing these claims that like various companies outperform humans, and as vague as they sound and as little as people tell you about what's happening there, they seem to be real. Like if you look at their evaluation charts and performance charts, they do seem to be outperforming humans, even though it's like almost impossible to extract like any kind of precise information about what they're actually doing there. And that's why part of my talk today will be about working with completely black box models and how even those have privacy issues, that even if you don't know what's inside the box, it can still leak a significant amount of information. And I'll try to talk to you about how you can take advantage of that. Let's see. So by and large, the tasks at which modern machine learning is very good. And okay, sorry, just one disclaimer. So let me go back here. Almost all of these incredible techniques that people use that produce these amazing results are all based on so-called deep learning, okay? Or artificial neural networks, which people these days use almost interchangeably. Of course, machine learning is a huge field, and there are lots of techniques that people have worked for years with all kinds of guarantees. And yet, like, I mean, they are being used to some extent, but by and large, what people use in industry today is deep learning. So even though I try to understand and think about privacy problems generically, in machine learning generically, without being married to a particular technology, it will be important for us to understand what deep learning is and how people are using it, because that's going to motivate a lot of what I'm talking about. And that's kind of hard to avoid, because if you worry about privacy problems in the real world, things that people are struggling with, you kind of have to engage with deep learning, because for better or for worse, that's what people do. Even though there is relatively little theoretically that can be said about it. Although maybe Adam will take an issue with me saying that, but you know. Let me put it this way. The theoretical abstractions that people use to talk about deep learning seem to me pretty far from what's actually happening when people use deep learning. All right, so let's now come back to the kind of things we're dealing with here. A typical task at which deep learning is very good is something like classification, okay? So a lot of these successes of deep learning that have to do with image recognition and object recognition and all that, they come from like casting these problems as classification problems and then training neural networks to deal with that. I'll show you how neural networks are trained very superficially, but I'll show it to you in a few moments. But for now, let's just kind of abstractly think about, you know, what is it that they're trying to do, and what do I mean by saying that it's a classification task? So the process works something like this. It starts with taking a training set, ideally a very big training set, but as we'll see in a moment, unfortunately, it's not often big enough. So you take this training set, and then you train a network, and the training could be supervised or unsupervised. So maybe you all know what I'm talking about, but nevertheless I have to say it anyway, just so we're on the same page. In supervised training, there would be lots of examples, and they would be actually labeled with their correct class. So for this, for example, we have a very standard classification task, which is object recognition, where the goal of the system is to try to recognize the type of the object in the image, like to distinguish, you know, planes from trucks, from horse carts, and so on. So in supervised learning, the training set would be just a whole bunch of examples which are labeled with the correct label. Or maybe if your goal is handwriting recognition, each one of them is going to be labeled with the actual text that's in it. So my understanding is that every time you solve one of those annoying CAPTCHAs, you're actually contributing to the training set for the systems. And once the system is trained, when it operates, you give it an image, and then some magic happens inside, and it gives you what it thinks is the correct classification. Here is what's very important about this, and this is going to be really essential when we talk about privacy during the second hour. These systems just don't give you like one answer. They don't tell you like, I think this is a car, okay? Instead, they give you a vector over all possible classes, and they assign a number. You can interpret that number as a probability. So they all sum up to 1 somehow. So to each possible class it assigns a number, which sort of tells you how confident it is in its prediction. So in this case, you can see it's pretty confident that this is an automobile, but maybe there is a chance that it's a truck, so it's a lower confidence. That's not the prediction, but you see this number associated with a truck, and maybe other categories have lower probabilities. That's kind of pretty essential, because through its output, the system is telling you how confident it is in its classification, and gives you, and not just for the most important classification, it sort of gives you other possibilities, and how confident it is in them. Okay, now let's talk a little bit about what's actually inside of this thing. In this day and age, it's mostly these neural networks, namely deep neural networks. What makes them deep is the presence of multiple layers. Actually, in modern kind of industrial strength neural networks, we could be talking like hundreds of layers. You know, that's what like Google and Facebook run. Which are wired, connected to each other in some fashion. The details of this are not like super important, and they actually like vary from system to system, and there are different ways of programming them. But roughly, it's this kind of computation where you put some input, and the initial layer looks at very local features of the input. So maybe it's looking at like individual pixels or neighborhoods of pixels. And then the further you go into the network, the computation that is being performed is very simple. So you take, at each layer, you take the output of these nodes that you have over there, and each connection there, each wire has a weight attached to it. Yeah, I know, like why is this not on the picture? Yeah, sorry about that. So there is a weight attached to it, so effectively each node is computing a weighted aggregation of the nodes in the previous layer. Okay? And then the computation propagates like this towards the final layer, and in the final layer it produces the output of the network. But that's all it is. It's like some kind of weird wiring pattern and then just a whole bunch of aggregations moving forward in the network. Okay? And you can even give some interpretation to what is being recognized at different levels of the network. Maybe at lower layers, it tends to recognize very local features, you know, like little gradations in pixels, little pixel neighborhoods. In the middle of the network, so this is a facial recognition model. Like in the middle of the network, it's recognizing now like kind of parts of the face, like a nose, ear, so you have much higher level feature. And towards the output of the network, you start having like really high-level features like a face. And facial recognition, by the way, is one of the tasks at which neural networks are exceptionally good and seem to be significantly outperforming all other techniques that have been proposed to date. So that's roughly the idea. So very simple computation and propagation of input of data from input to output. But one thing you should see here right away, and that's actually the important part, as you'll see in a moment for privacy, is that unlike many other machine learning models you're going to see, there are a lot of parameters here, like a lot. So if every wire has a number assigned to it, a weight, okay? And you have like a 100-layer network and every layer has 100 nodes, well, I don't know, somebody here who is better than me at combinatorics can calculate the number of parameters, but like a lot, okay? Like this much. And that turns out to be important because, well, you'll see, I'll keep you in suspense, but you'll understand why this actually happens to be pretty important for privacy. Okay, good, I actually do have some kind of picture, but it shows just at one this is kind of a zoomed in version of this picture that shows at the level of one so-called neuron, even though it's not like a real neuron, it's some very simplified artificial representation of this. So there are signals coming from the previous layer, they're weighted, and then some very simple function computed. It could be like a step function, or, I mean, there is like a very small library of functions that people compute and then goes to the next layer. So the real action, so to speak, in the network is in these parameters. It's in these W values. Like the whole point of neural network training is to discover these W values that make the network perform well. And their standard notion of performing well is producing good classifications. Okay? How are these parameters learned? Well, it's an optimization problem, right? So you have a whole bunch of training data and you want to keep adjusting parameters until they're good for some measure of performance. So that's a standard optimization problem, which in neural networks these days is typically solved using stochastic gradient descent, which is a very standard optimization algorithm. So the goal here is to find the values of these W's on all the wires so as to minimize the classification error. And of course you could ask, well, how is this classification error computed? And we're talking about like supervised training here. Unsupervised is just a little more complex, but in supervised training, I mean, it's simple. If you have labeled data, you can run it through the network. You know the true label for every image in there or every sentence, whatever you're doing. So you know the true label, you know what classification the network assigns to it. So if they're the same, good. If they're different, that's your error. So you can compute the error on some batch of inputs. And the goal is to find these values of W that minimize the classification error. But what's important, there are a lot of them. As a matter of fact, there are so many of them that you could ask yourself a question. Well, let me walk you through the process and then I'll ask the question. Okay? So normally, kind of textbook representation of this neural network training process, and again, my apologies to those of you, and I'm sure there are many who have seen this like a million times before, so I feel like, why am I telling you this? But it is important for me to go through this so I can do the rest of what I want to talk about. So, okay, so how does this parameter training work? So you start with this feed-forward stage where you have your training data set, which is processed in batches. So you take kind of a batch of inputs, and for each input you feed through the network, meaning you just apply the network to like pixels of the image, and then just a simple weighted computation. These days it works very fast. We have special frameworks optimized for it. They're designed to run on GPUs, so there is a lot of intelligence and systems invested into making this super fast, and then it propagates from input to output and produces some kind of output in the back. And then we look at the output produced by the network, and we compute the error, which is, since it's supervised training, we know the truth, and we know what the network produced. That allowed us to produce the error, to compute the error. And once we have that, we actually solved the optimization problem, which is adjusting these internal weights on the wires so as to minimize this error. Okay, makes sense. So you take this error and then you try to attribute it to each connection going backward. So that's the backpropagation stage, where you propagate this error backward. And somewhere in here I should have a picture of like a partial derivative, but maybe I don't. But that what?
Next slide.
Oh, next slide. Okay, thank you. Yeah. Good. Where's my partial derivative? Yeah, there you go. Okay. So that's again a very basic idea, is that you are just attributing error to different connections in proportion to the weight on that connection, and then you adjust weights so as to minimize the error on this contributed by that connection. And you keep doing this millions and millions and millions of times until you finally achieve good performance. So now let me ask a question that I want to ask. So here is something to which I don't know the answer. Like, so how to ask this question? So, like, computationally, okay, this process is solving some optimization problem, and it's usually called learning, as if the network is actually learning to perform some recognition task with minimal error. But in reality, like, the number of parameters here is really, really vast. Okay, so we're talking like, you know, squillions of parameters, if that's a number. And what if this thing is not actually learning, but what if all it's doing is encoding its input in the weights of the network? Okay? That's kind of like a strange way, like why is that, like, I wouldn't even call that learning, but somehow like the memorization capacity of modern neural networks is immense. So there is really nothing stopping it. And by the way, every weight is, just so you understand, that's like a floating point number, okay? I mean, it could be, its precision could vary, but there is a lot of information in each weight. And at some point, I did the following experiment. And this is not on the slide. I'm just kind of sharing just to show you like the power of this thing. So I thought like, well, can we maybe build like, just, you know, out of curiosity, a malicious neural network? So what does mean malicious neural network? A network that actually performs well on its inputs, but as sort of just to leak information about its training data set, it encodes like training data set in its weights, okay? While performing well. And it turns out that if you take like a modern network and a standard training task for something called CIFAR, which is a standard object recognition task, just with a very simple like encoding technique, nothing smart, you can take like a quarter of the training data set, so like a lot, like huge chunk of the training data set, and encode the entire training data set, like every pixel, right? So like full information. I'm not even talking like extracting anything sensitive from it. Like a quarter of the entire training data set on a standard evaluation task could be encoded just the least significant bits of weights, which sort of tells you that somehow this thing has like huge like memory. So who knows? Anyway, that was kind of an aside, but who knows what it's really learning when we talk about learning. But that's how people do it. Oh, no. Sorry, I forgot about this. So it actually performs well. So my trick is I can encode like a quarter of the training data set, and it still performs like very, very close to what it performed like if it were trained through the normal process. That's a very important point. Yeah, yeah. Yes. Sure. But I'm, you know, as always, I'm interested in what, like, you know, people do in the wild, right? And in the wild, you often see that they throw, like, highly over-provisioned models onto problems with relatively small training data sets. And the reason I'm talking about this is kind of I want to set the stage to the, like, privacy question, which it'll take me 2 hours to, like, get to the real question, but, like, who knows what the hell is stored in these networks? Like, as a result of this training process, like, we don't actually know very well what exactly it's learning. We know that it's learning to perform its primary task well, but we don't know what else it's learning, and I'm just trying to tell you that there is a lot of memory here to remember things. So that's the only point I'm making, like, this minute. You had a question? No, there was... So, no. Totally. It's, I'm not saying, like, all I'm saying is that a network could remember a lot of things and that would not impair its performance on its primary task, okay? That's all I'm saying, that there is a lot of memory in this thing. And who knows how this memory is being used, and maybe, and I'm like jumping ahead a little bit, an interesting question would be to try to extract whatever it remembered while training. Because who knows, right? Who knows what it remembered? Maybe there is something fun in there, okay? That's correct. Well, I mean, I don't know about we don't see it. Like, if we don't look for it, we don't see it, okay? But there are lots of things in my experience that you only see when you look for them. You're like, oh, wait a second, oh, that thing, okay. So that's the only point I'm making here, but I'll give you more. Okay. Right, sorry, yes, I was still talking about this training. So, and that's your stochastic gradient descent right there. That's adjusting parameters based on how much they contribute to the error. And of course, like, when people do it, I'll just mention this is not super important. Well, it is kind of important, so I'll mention it. In reality, I mean, they don't just do like pure stochastic gradient descent. I mean, there are, in real network training, there are like all kinds of tricks and all kinds of techniques that people use to prevent gradient descent from getting stuck in local minima, right? So they would randomize things. Occasionally, when they do this training process, they would just drop some updates, okay? They would just like, this is known as like dropout technique, which actually turns out to work pretty well. They would just ignore some updates, or they would add some randomness, some stochasticity, like in random places. So they try to kind of jog this process to prevent it from getting stuck. There is like a huge armory of techniques that people use when these things run for real. And there are people at like Google's and Facebook's who are paid like millions of dollars because they know how to tweak it just right. For each batch of training data, this optimization process tells you how much each parameter needs to be adjusted, by a little, by a lot, up, down. So you do this adjustment, and then you do it again. And then you do it again, and you do it again. And then, fingers crossed, the process converges, meaning that these adjustments to parameters become smaller, and at some point, parameters are not changing anymore. Why does it converge? I think nobody knows. This is kind of one of those mysteries of life, like, you know, why it, yeah, but it does. Empirically, it does. And as far as I know, like everything here, like there are no guarantees here, there are no theorems except like in very simplified abstractions. But like, why do massive models that like Google runs for image recognition, why do they converge at all? It's, you know, kind of one of these divine gifts to humanity, so we don't know. But they do converge and they do produce these very high-performing models. All right, so now let's talk a little about privacy. Now, like, that's kind of my angle here. I'm not a machine learning person at all, as should be totally obvious from this rant. So I don't really know much from machine learning, but but I do want to understand its implications for privacy. And implications are actually fairly substantial. Even as recently as like a couple of years back, when I wanted to talk about privacy of users' data, it was kind of pretty simple. So, okay, so some company collects data from users, and that's actually what I talked about on Sunday. I think, yeah, on Sunday. You know, some company collects data from users, and then the data is like either shared with advertisers or used in some form inside like a service or an app. Okay, that's the standard way of using data as of like 2-3 years ago. And you can ask like all kinds of interesting questions, such as, you know, what happens to sensitive data that is being collected? Can you anonymize it successfully? Is there such a thing as taking a data set and removing identifiers? And the dual of that question that I also talked about on Sunday, can you re-identify an anonymous data set and what you can do? There is the whole topic of inference attacks that I briefly talked about, which is, okay, so suppose I'm not publishing the data, I'm using it inside some system. Can I learn about this data by interacting with the system? Okay, suppose I'm not publishing the data, I'm publishing something correlated with the data. Can I exploit these correlations to reconstruct something about the data? So there are all kinds of interesting questions you can ask, and actually many of them are answered very well by differential privacy, and so on and so forth. But that's the world of yesterday. Okay, maybe of today, but soon to be the world of yesterday, because using raw data is very difficult. It's sort of like you need to parse it, you need to understand what it does, you need to do a lot of processing before you can get anywhere. And that's why in the very near future, we're going to see machine learning as kind of a very essential component of this data processing pipeline. That is, companies are not going to be using just raw data. They're going to take machine learning and they're going to apply it to the data, and then whatever machine learning is going to give them, they're going to use in their apps and services and so on and so forth. Now, machine learning is like very abstract. I mean, I'm not saying they're going to use a specific algorithm, but they will try to process data in a way that gives them, you know, the usual purpose of machine learning, that gives them some essence of what they want to learn from the data. And the interesting aspect of it that I'm going to spend some time talking about is that to apply machine learning, they would not even need to know what machine learning is. Because machine learning is kind of a hard thing. There is like math involved and thick textbooks and smart people. And for typical like practitioners who just, you know, collected a bunch of data from like app users and want to figure out like what to sell next, you know, they're not going to go and read like Vapnik's book or something. So they just want something quick and dirty. And that's why machine learning now is being packaged as a service. So big companies like Amazon's and Google's, they're providing this very nice service to their customers where you can take a data set, you can take a task like, okay, tell me, you know, how to cluster these users, or tell me like how to predict what my user is going to buy next. So you can just upload the data set. It goes into, you know, some happy place in the cloud, and then you push a button, you pay a few bucks to Google, and Google gives you a model. Google doesn't actually give you a model. They give you, I'll talk to you about what they give you. They give you an API access to the model, but the point is you can outsource all of that machine learning intelligence on your data to somebody else who you hope knows better than you do, and they'll build models for you that then you can use inside your services. But it's kind of like brings us to a very interesting world where people who are using machine learning are not actually like really like understanding anything about machine learning. And there is no control over like what data sets they're going to use. Are they going to set up meaningful classification tasks? All of that is beyond, I mean, they're going to do what they're going to do. And this way of using machine learning, kind of machine learning as a commodity, is interesting because it raises all sorts of questions. So one question that I will be answering for the next hour and a half is this question, is do trained models leak sensitive data? Okay? And I'll keep this vague for now because that question was actually vague for many years, but there is the sort of idea like a model is based on data. So can I learn the data by talking to the model? So that's one question, but Another very related question that I hope like Kobe is going to answer later today is it possible to train a good model for whatever notion of good machine learning people use, typically expressed in terms of some kind of utility, some kind of predictive power, while respecting privacy of training data? And again, neither good nor privacy is defined here. So maybe today we can make this a little more precise. So that question will be addressed. And then there is another question that I think nobody is going to be talking about today, but I'll just put it out as an interesting question. If I'm giving somebody black box access to my model, is it possible to keep the model itself private? That is actually like a very meaningful question, but I will not attempt to answer it today. Okay, so now let me focus on the first question here, which is, do trained models leak sensitive data? This brings me to an important paper in this field, which is a paper on model inversion. It's actually not one paper. There are 3 papers on model inversion now, and maybe more in the pipeline. So this but the first and famous one was published in 2013 at Unix Security, where it received the Best Paper Award, which is a sign of respect and recognition and glory in the security community. So model inversion is poses the following like sort of very interesting problem, which is this. So we know that we have a model operating on some data, and maybe okay, so like in this case I guess it's a facial recognition model, but it could be any kind of model. And then they ask like, okay, if I look at the output of the model on some input, can I infer something about the input? Okay, on the surface that's a very plausible looking privacy question. Okay, you give me an output of the model applied to some input. Can I learn something about the input? Maybe I can learn something sensitive. Maybe I can learn something very that people don't want to know about this. This something is a little vague. In the paper, they define it as unexpected attributes. Okay, so can by looking at the output of a machine learning model, can I learn unexpected attributes of the input? Like, you can stare at this definition of, I don't know, that's not a definition of privacy, that's kind of that's the definition of privacy breach. A privacy breach occurs if given the output of a machine learning model, I infer an unexpected attribute of the input. Okay? So it's already like a bit of a weird definition if you think about it, because like unexpected by whom? I mean, it's sort of like, it sort of assumes that the adversary has certain like expectation of like meta expectation of what they might be able to learn, and then like, oh boy, I learned something else here. That is actually never defined anywhere in the model inversion literature, what unexpected is. But there is something strange about this whole setup. So they give a very powerful illustration in their paper of how model inversion might work. And that's the infamous Warfarin example. So let's try to work a little bit with this example so that we try to understand like what exactly their privacy definition is saying. So what's the modeling task here? This is the modeling task. So it turns out, and this is one of these big successes of personalized genetic medicine, that there is a drug called Warfarin for irritable bowel syndrome or some disease. And it turns out that the dosage of that drug can be determined by looking at the genetic makeup of a patient. So patients with a certain genetic makeup need like a particular dosage. People with a different genetic makeup need a different dosage. And there was a study in some clinic where they took like patients and look at their genomes and sequenced these genomes. They did this study where they determined this model. Effectively, what the model is a correlation between genetic makeup of a person and how much of a drug you need to give them so that they react well and don't die, which is obviously a good goal. Well, model inversion asks a question. Well, can we, maybe this whole thing is privacy breaching. Maybe by looking at the output of this model, we can infer something sensitive about an individual. What is more sensitive than the person's genome? It's an immutable characteristic. It's correlated with God knows what. Maybe we can infer information about the person's genome by looking at the output of the model, which here happens to be the dosage. And then they make the following observation, that this model that predicts what dosage somebody would benefit from given their makeup is actually privacy breaching. It contains a substantial privacy breach because if you know this model and you know somebody's warfarin dosage, you can invert the model. You can run the model in reverse, so to speak, and figure out what their genetic makeup is. Okay? That's the definition of a privacy breach. They got a Best Paper Award for discovering this breach. Okay, so this sounds like one of them seminal results in the history of privacy. Yes, Benny?
Sounds odd, but it seems like a trusted party that gives you the right dosage. And assuming that it seems like a feature of the dosage, not the model. That is something wrong.
The model is correct in terms of utility, but what about privacy? I mean, they're claiming, sure, it's a correct model, but it breaches people's privacy because now the model, like, tells you, and actually, it's interesting, like, they position it. It violates privacy of people in the study, okay? Like they you know, there were 1,000 patients from whom this was collected. I mean, on whom, what?
Just the privacy of those in the study, not everyone else.
Well, okay, so observation number one. That's like a pretty weird definition of privacy because, like, according to this, definition of privacy breach, according to this, if that's a privacy breach, I mean, it violates privacy of people in the study. It also violates privacy of people who have never been anywhere near that study, who are just prescribed the drug, and by looking at the dosage of the drug, you can infer their genetic makeup, okay? So, like, it's... You can, if there is a model. So now, okay. So now let's find more privacy breaching models. So now if somebody finds genetic basis for a certain type of cancer, and we all know that some cancers have genetic basis, boom, those models breach privacy as well, okay? Because now by looking at certain type of cancer, you can run the model in reverse and infer, well, boy, that kind of thing is genetically determined, so I'm inferring thing about genetic makeups. So it looks like this privacy breaches are pretty ubiquitous, yeah?
Isn't the fact that the person, you know that a person is taking this drug, given that it's sort of like, it's not even ML inversion, it's sort of like a rainbow table. I know that this person has this warfarin dosage, 3 milligrams, that means their genetic makeup.
So now you're saying something different. Is maybe the model is actually fine. Like the real problem is that if you know somebody's dosage, then you can use the model to infer additional things about it.
Not even a model. Just go back and say, at 3 milligrams, chances are this person's genome makeup.
Right. But this, if 3 milligrams, chances are, that is the model. That's exactly the model you're using at that point, like for that inference, right?
I think the bigger privacy breach is the fact that you know that this person is taking it once. You know a person's taking it, it's not a huge...
Okay, let's talk more. So Antonio, then in the back there.
I guess the point, like, okay, an ideal model would be learning the correlation between your genome and your dosage.
Right.
And now you're saying, like, this is not a problem with the model. It's not that by using a better model or like a model more succinct with less like memory.
Sure. But you're right. I mean, that's all this model is. This is a super simple model. I mean, that model is just a simple correlation. So as a result of the study, they just computed the single correlation. So now we're in this weird world where, like, I'm saying correlation breaches privacy. Like a statistical fact is privacy breaching, which already should give you a sense that something is like wrong here. Yes. What? Correctness of the model, right. Okay. See, it doesn't make sense. Okay. So, and interesting thing, it's like it doesn't even matter that it's a model. Like this correlation between genetic makeup and dosage is a scientific fact. Okay. Maybe I didn't learn it by machine learning. Maybe I learned it because like I found an ancient book of wisdom that tells me this thing, you know, about humans.
Medical textbooks breach privacy.
No, like if you think about it, if you take it, like now medical textbooks breach privacy. Now like science breaches privacy. Okay?
That's why we need less of that.
I have a place for you in the new National Science Foundation.
Trump is in favor of privacy.
Yeah.
Trump is in favor of
Okay, there was another question in the back. You no? Okay, yeah.
Okay. I just following this line of thought, I want to make an extreme example of your response. I mean, imagine a very simple linear regression model, which is one-dimensional. So, me and my
Actually, that is a very simple linear regression model. Yeah.
me and my body go give our genome, so we get a couple points, we get a warfarin dosage amount. So we got the whole model. And now, if I know your warfarin amount, I know for any.
No, but that's exactly, I mean, you're just describing this. So now, working with this very plausible looking definition of what privacy for machine learning model is, we ended up in a place where, like, medical facts, like statistics, are all like privacy breaching because guess what? They enable you to like learn things, okay? They enable you to like infer things. Well, wasn't that the whole point of like discovering them in the first place? That you discover some correlation and then by looking at the output you can figure out what was in the input. So I promised you, like I showed you that L diversity picture, you know, long time ago. So here is a chart where they measure privacy disclosure. So it comes to us straight from that paper, and I invite you to like look at this chart. Okay. I'll stare at it too, so that it's in front of me as well. Okay. So. And here is my question to you. So what does this chart actually measure? So this chart is intended to show you how privacy, basically the extent of privacy breach. And actually you can see another thing on it. Like they try to apply differential privacy to the model. They got like very noisy results. The conclusion from this was that differential privacy kills people. Okay, that's how it was presented. I'll let somebody else like address that point. You know, I have no dog in this fight about differential privacy killing people. But yeah, right. But look at the like this thing called disclosure, right? So what does it actually measure? So it turns out that what it measures is basically the strength of correlation. Okay, so like what they call disclosure, like I would call science. Okay, and basically their disclosure is like the more like science you do, the more you learn about like patients. Okay. So like that is a remarkable chart, is because somehow like they just take like the quality of knowledge that you discover by applying machine learning, call it disclosure, and shows that how like the stronger the correlation, the more you learn, the worse the privacy breach. Okay, how did we end up in this place? And I hope you all see why this cannot be a workable definition of privacy. Anybody? I mean, am I convincing? Yeah.
I want to challenge you.
Oh, please do, please do.
Seriously, how come this got a
No, you're not challenging me. You're not challenging me.
I am, because you know more about it than I do. And it's really, I don't understand. How can you really think that this is like a breach of privacy? They're not all.
Well, I don't know. If if I say so myself. Okay. Well, I don't know. Buy me a beer. I'll tell you later. Okay. This is not. I mean, this is a lecture. This is a winter school. I can't say things on stage that I can.
Being filmed and
It's being filmed, right? Who knows who is watching this? So, but let me make actually a positive point. Is the motivation for this work, and that motivation is like explicit. It's like what like the paper says right there. Is that their concern wasn't about showing that like science kills, okay? Their real concern was that, you know, a bunch of patients in some clinic somewhere were taken, their genomes were sequenced, information was learned about them and so on. Their concern was about privacy of the patients in the study that was used to compute the model, okay? And I think that is a totally legitimate motivation, because that is something we could worry about, like, you know, how well do we protect privacy of patients that we use as like guinea pigs for our like machine learning models? So I hope nobody here will challenge that as the motivation. The way they framed it is strange, because like when you think about model inversion as a privacy attack, it applies to people in the study, because of course you can do this process of going from dosage to something for people in the study, but it also applies to people not in the study. It just applies to like humans in general, or to humans with a certain disease. Yeah. No, I'm not saying it should. I'm saying this is a misunderstanding. I mean, they start from wanting to protect.
not everyone's clear that you're being sarcastic.
I'm never sarcastic. Me? Okay, no, sorry. I'm okay. All right. Okay. Let me make my point clearly. So, I think the motivation of protecting privacy of people in the study is a good motivation. This definition of privacy is inspired by that, but does not actually do that, okay? It's not a workable definition of privacy, in part because it derives exactly the same conclusions about people in the study as it derives about people who are not in the study. So even though the motivation is good, this thing about by looking at the output of a model, I learned something about the input, and that breaches privacy cannot be a definition of privacy because, for example, it does not draw a distinction between drawing about people in the study, drawing conclusions about people in the study and learning things about people who are like nowhere in the study, okay? And that's like, and I would go like one step beyond that and say that drawing conclusions about like population, like generalizable facts about the population, that's the purpose of scientific discovery, okay? That's why we do science, that's why we do statistics, that's why we do machine learning. And apart from this like thing about unexpected attributes, which is never defined, like it's not even clear like how to distinguish between scientific facts that are privacy breaching according to this definition and not privacy breaching, okay? And therefore, I would argue that this is not a workable definition of privacy, okay? Plausible as it looks, or maybe after I bashed at it for a while, it's no longer being plausible, but it's not, okay. So I have a picture for that. Kind of when does inference breach privacy? So somehow, like we take some training set, which is a sample from the population, we're gonna construct a model from it, and then we're gonna draw conclusions about the model. And we can draw conclusions from the model that are true about the population. And we can draw conclusions, and by the way, like since your training sample is part of the population, the conclusions you're gonna draw about the population, they're also gonna apply to people in the training set, just because they're members of the population too. And then there are conclusions that you're gonna draw, that you can only draw about people in the training set, that are only true by virtue of these people being included in the training data set. And like, it's very, like, mixing these two is kind of a bad thing, because you can paint yourself into a corner where just like any conclusion you draw about someone breaches privacy. Let me now talk, let me see what time it is. Yeah, I have 5 minutes. Let me talk a little bit about another like model inversion 2.0, okay? Which actually achieved something interesting. That is not on the slides at all. So I'll have to maybe draw at that point. So here is how they do model inversion in 2.0. Okay. Let's say we have a model for facial recognition. So what does a model for facial recognition look like? You have a training data set, which are just like a bunch of faces like of the same individual, okay? Yeah, obviously I'm not like drawing very well here, but so you have a bunch of faces of the same individual, and then you train a model based on this. And actually, sorry, this is like one class, so this is individual number 1, and then there is another individual, and you have like his faces too, okay? And then there is a third individual, and you have like his faces, okay? And the model learns to distinguish. So given a model, you give it a face, and it tells you like 1, 2, or 3. Okay? So here is another way of using model inversion. Take this model, then set its output. You say, it gives 1, 2, or 3 are output, and you tell, let's imagine the output of this model is like 100% on 1, 0% here, 0% here. Let's imagine that the output of this model, it's very confident that this is person number 1. Now let's run the model in reverse and see what it produces as an input as you run in reverse. And it turns out that when you look at what it produces as an input, it actually looks very similar to person number 1. And they say like, boom, I am recovering training data. See? Like, and they actually have very concrete experiments for this facial recognition model where they set its output so that it predicts a particular class, and they do it for facial recognition, and then they run it in reverse, and they get a picture, and they show you the picture, and like, damn it, that totally looks like, you know, this ugly looking, yeah. Which now sure as hell sounds as recovery of training data. That's a little...
What face recognition task are they doing? They're trying to recognize a specific person?
A specific person. So the model is trained, there are like 40 classes here, which are for like different people. The training examples here are all different pictures of the same person, okay? And the task of the model is, given a face, recognize which of the 40 people it is. That's the task. And when they set the output as like, I'm really confident that this is person number 5, run it in reverse, they get an input that looks like person number 5. And like, no denying it, he does look like, kind of like person number 5. And that, they say, is recovery of training data. So I know we're almost out of time, but like bear with me for like 10 minutes, because this is important to understand what is really happening here. Yes?
Right, so, well, I guess I'll let you, as a crypto person, my instinct with this problem is saying, is to say that, the assumption here is that they're proposing these models are thought of as essentially like non-invertible functions, and the issue is that they are in fact efficiently invertible.
They are in fact efficiently invertible. That's true. That's true. But let's talk about privacy. Okay? No, you're absolutely right. I mean, it's not clear like why it's bad that they're invertible. Okay? And they're saying it's bad because it allows you to recover training data by running model inversion. Okay, unfortunately, and this is my fail, I should have put it on the slides. I cannot show you like the actual faces, and I cannot draw them, well enough and fast enough. But this face, there is something very weird about it, and there is a little like kind of, bait and switch going on. What? So this face that they recover for this class, he does look like training faces. The key word here is look like. Okay? In a very strange way, this face is actually not one of these training faces, but somehow like their average. Okay? So what model inversion is doing here, and it's subtle. It took me a while to like really understand like what it's doing, and actually I didn't. Actually, Adam explained it to me, although he's been denying it ever since. Is that when you run model inversion here, it recovers features that define a class. Like somehow in the internal representation of this model, there are like certain features that make it think this is a representative of class 1. There are certain features that make it think this is a representative of class 2. And actually, if it's a good model, chances are these internal representations are separated. That's what makes it a good model. So what model inversion is doing, it's recovering the features that characterize class 1 and outputting those features. For a facial recognition model, like these features that define a person, they kind of look like a person. That makes total sense, right? For a facial recognition models, this is somehow the average of the training faces. They're not actually recovering a point in the training data set. They're recovering the features that all the points have in common. And that's where beta switches. They tell you, oh, but we recovered the face, and that looks just like that guy. And he does, because like all points in the training data set look like that guy. So visually, any combination of features that define that class is going to look like that guy. But that's for facial recognition. Now let's imagine some other task, like object recognition. You recognize like trucks. Your goal is to recognize something that looks like a truck. When you run model inversion on a object recognition model, what do you think is the output of model inversion on the class called trucks? Well, something that looks like the average of all the trucks the model has seen, okay? It's basically the features associated with a truck, but these features are so abstract in case of trucks, it actually doesn't even look like a truck. It sort of vaguely looks like some shape that is maybe a truck, but it's certainly nothing as recognizable as the face, which is the average of the faces of the individual, and it's totally clear that is not a point in the training data set. That is just like the representation, visual representation of features that define a particular class. There is no recovery of the training data happening here at all. It's not recovering training data. It just gives you a visual representation of what the class looks like, which is actually not specific to any point in the training data set. And as a matter of fact, is true also for points outside the data set. Just a second here. Like, I really wish I had pictures to show. Actually, I do have pictures to show, but
The whole point of such a model, though, is to not preserve privacy because you want to be able to recognize a specific person.
that's right.
If you try to
Exactly.
differential privacy feature, then you'd want it to be whether the person was in or not in you.
That's right. It's because like that's a very specific task where like the entire class looks the same, okay? And the whole point of the class is to recognize what it looks like. So the definition of the class is the face of that person. So it's not like recovering training data set. It's not doing anything. It's just like a really well-chosen model to kind of make you think that they're recovering training data. Yeah, sorry, you had a question. Right. So I wish I could show you a picture, but unfortunately it's like on my laptop, and this is not my laptop, so I'm not going to show you a picture. But I have some very nice pictures that show the result of model inversion on classification tasks where the class is not defined. I mean, is not like where all training inputs don't look similar, and it's, oh, that went flying. And that looks like a blob, okay? It just doesn't look like anything. It's just like some averaging of features and so on. So that's what model inversion is doing here. Okay, so there is Frank McSherry's blog post that I recommend highly. It's called Statistical Inference Considered Harmful, where he kind of makes all the points I made in this lecture today in a very kind of frank kind of, you know, no holds Bart type of way, but it's a nice blog post to read, where he takes model inversion to the woodshed, so to speak. All right, so let's maybe break, and we'll continue with a better definition of privacy in like 15 minutes, okay?